She had exactly 11 days to be gone. That number came folded inside an envelope, left on the kitchen table by her son Heinrich on an October morning in 1889, as though the eviction of a 72-year-old woman from a house she had lived in for 31 years was a transaction that required paperwork. 11 days take what you can carry, vacate the farmhouse, and relocate yourself at age 72 in the Bitterroot Valley of Montana Territory, with 6 weeks remaining before the first hard freeze, into a 3-room storage cabin sitting 200 yards up the hillside from the main house that nobody had wintered in since 1878. The cabin had no stove. It had no insulation beyond the original log walls, and those had been chinked with river mud that had dried and cracked over the intervening decade, leaving gaps wide enough in places that you could push 2 fingers through and touch the outside air. The roof leaked in 3 places. The door frame had shifted enough that the door no longer closed flush, and it was one building alone. The other 2 structures Dorothea Krause would eventually connect to it were a tool shed and a root cellar annex, scattered across a low hillside 40-odd feet apart, fully exposed to the northwest wind rolling down from the Bitterroot Range. What she built between that October morning and the following February is the reason this story still exists, preserved in a letter her granddaughter Elsa wrote in 1921 to a cousin in Wisconsin, describing what the ranch hand Arvid Sjöberg had told her about that winter. Elsa had walked the hillside herself that year. She had seen the tunnel openings. She had pressed her hand against the sandstone channel lining and felt what 30 years of Montana winters had left unchanged: warmth from below. To understand what Dorothea was walking into, you need one specific number first: 32 degrees Fahrenheit. That is what the Missoula weather station situated in the sheltered valley floor, not on the exposed northwest-facing hillside where her 3 structures sat, recorded on January 14th of that winter. The Missoula station was protected from the worst of the Bitterroot wind by the valley topography. The hillside was not. Wind sustained at 25 miles per hour at minus 32 degrees Fahrenheit produces a wind chill of approximately 65 degrees Fahrenheit. At minus 65 degrees Fahrenheit, exposed skin freezes in under 2 minutes. A bucket of water goes solid in 45 minutes. Cast iron, which Dorothea's sons considered the gold standard of frontier heating, becomes measurably brittle. And any gap in a wall, any crack in a chinking joint, any open seam between a door frame and its jamb, becomes a channel through which heat bleeds out of a room at a rate that a fire can barely replace. None of that had changed since Heinrich wrote the number 11 on his piece of paper. He knew what Montana winters were. He had lived through 31 of them in that house, fed through every one of them by his mother, and he wrote 11 anyway. Dorothea Krause had been born in Bavaria in 1817. She had come to America with her husband Franz in 1851 and had followed him west to Montana Territory in 1858 when the gold strikes at Bannack were pulling settlers overland by the thousands. Franz was not among the men chasing gold. He had looked at the photographs and the accounts, and what he saw was not the ore, it was the grass. The tall, dense bunch grass of the Bitterroot Valley floor, a grass variety he recognized from Bavaria as an indicator of the kind of deep, water-retaining soil that grew cattle through hard winters. He had been correct. By the time he died of a stroke in August of 1889, the Krause Ranch was running 340 head of cattle across some of the best natural pasture land in western Montana, and it had the only working hay press in a 30-mile radius. Franz left no will, not because he hadn't thought about it, but because in Montana Territory, in the late 1880s, among German immigrant farming families, a written will was not always considered necessary. The eldest son knew what was expected. The property passed, in practice and soon enough in law, to the male heirs. Under Montana territorial law in 1889, A widow was entitled to a dower right 1/3 of the real property her husband had owned. The remaining 2/3 passed to the male heirs. Franz and Dorothea had 2 surviving sons. Heinrich, who was 47 and had been running the day-to-day operations of the ranch for 6 years, living in the main house his entire adult life. And Wilhelm, 44, who had left for Butte several years earlier, working the mining industry there, and who came back for Franz's funeral in August and apparently never quite made it back to Butte in the weeks that followed. What happened in the conversation between the funeral and the envelope is not recorded. Elsa's letter does not speculate about it. What the letter records is the outcome. Dorothea was told, by her sons acting together, that her continued presence in the main house was inconvenient. That was the word she used when she described it to Elsa's source, Arvid Sjöberg, inconvenient. After 31 years of running that household and keeping the ranch accounts in a ledger, Heinrich still used as his operational template. Her legal option was to pursue her dower right through a territorial court. In practice, that meant waiting for the circuit judge, who covered an enormous territory and might not pass through that county for 6 months. During those 6 months, she would need somewhere to live. The offer on the table was the storage cabin, use of the root cellar, and 1.5 cords of already cut firewood, and she took it. 1.5 cords of firewood, stated plainly, is a stack 3 feet wide, 4 feet high, and 12 feet long. For a single average-sized room in a Montana winter, you need between 5 and 7 cords, depending on how well sealed the structure is. For 3 structures on an exposed hillside, 1.5 cords was not a supply, it was a prop, something Heinrich could point to if anyone asked whether he had provided for his mother. When the wood ran out, she would come back to the main house on his terms, or she would not survive. He had not, when he wrote that number on the paper, considered the possibility that she would find a third option. Dorothea spent her first 3 days in the storage cabin doing something Arvid Sjöberg later described to Elsa as walking the ground and counting to herself. She was not wandering. She was measuring her walking stride, which she had long since calibrated to approximately 28 inches, serving as her instrument. Distance between the main cabin and the tool shed, 38 feet. Distance from the tool shed to the root cellar annex, at an angle across the hillside, 44 feet. The position of each structure relative to the northwest wind. The main cabin had the hillside rising behind it to the northwest, which gave it some break. The tool shed was fully exposed. The root cellar annex sat in a slight depression that the wind curled down into rather than over. She also dug not to excavate, just to probe, using a sharpened fence post she had pulled from the collapsed south side of the tool shed perimeter. She drove it into the ground at 8 to 10 spots across the hillside, in between and around the 3 structures, and she felt for something specific, the depth at which the soil changed character. She found it consistently between 13 and 15 inches. Above that depth, the soil came off the post dry and crumbled and slightly gritty, the freeze-cracked, seasonally active layer that responded to weather the way a sponge responds to a hand, absorbing cold in winter, warming in summer, never settling. Below 13 to 15 inches, the soil was different, denser, darker. The blocks it came off in held together instead of crumbling. And the fence post, when she pulled it back out of the deeper hole, was warmer to the touch than when it went in. That observation was not a novelty to her. She had grown up in Bavaria, watching her father dig root storage into the hillside behind their farmhouse. She had seen the specific way the traditional Bavarian keller, the dug-in cellar, typically excavated 5 to 6 feet into a hillside, maintained a stable internal temperature year-round. She had spent 3 decades watching the behavior of the root vegetables stored in the root cellar annex here. The way a potato stored at 12 inches of depth never froze even when the surface ground in January was hard as iron. She had noticed that the water in the deep well on the property was 48 degrees Fahrenheit every time it was drawn, whether in July or in February, and that it had never been otherwise in 31 years of drawing it. The earth below the active frost layer has a temperature that does not change with the season. It ranges from roughly 45 degrees Fahrenheit in the northern mountain states to 65 degrees Fahrenheit in the deep south, and it holds that temperature within 1 to 2 degrees through the entire calendar year. This warmth comes from below, from the slow, constant upwelling of geothermal heat through the crust, not from above. Surface weather does not reach it. A blizzard that drops the air temperature to minus 35 degrees Fahrenheit does nothing to the soil at 5 feet of depth. The soil at 5 feet is 50 degrees Fahrenheit on that day, on the day before and on the day after. It was 50 degrees Fahrenheit the previous January. It will be 50 degrees Fahrenheit the following January. Dorothea had not been taught thermodynamics. What she had was 72 years of paying attention to the behavior of the physical world around her, and specifically 31 Montana winters of observing what the earth did and did not do under temperature extremes. She had arrived at the same conclusion that soil physicists would eventually quantify in technical literature. Below a certain depth, the earth is a thermal reservoir, stable, reliable, and available to anyone willing to dig to it. There was also a specific problem with the root cellar annex that sharpened her thinking. The annex had been dug to approximately 4.5 feet, adequate for most Montana winters, but not for a severe one. In the winter of 1886 to 1887, the frost penetration in the Bitterroot Valley had pushed past 4 feet in February, and Dorothea had lost a third of her potato stores when the lower shelves froze hard enough to rupture the cell walls. She remembered that loss precisely, not as a general bad winter, but as a specific failure with a specific cause. The cellar had been too shallow for what the cold that year demanded. She had compensated by digging the lower shelf down another 18 inches the following spring, which brought it to just under 5 feet. That had held since. But she also knew from 31 years of using that cellar through Montana winters of varying severity that the current winter was already colder than average, and that the root cellar's margin above the frost line was narrower than she wanted it to be for a winter that looked like it intended to exceed 1,886. The tunnel connection she was planning would solve this directly. If she could bring pre-warmed air from the main cabin through the earth channel and into the root cellar annex, the cellar's temperature floor would rise not to 65 degrees Fahrenheit, because that was not the goal, and would in fact ruin stored produce by accelerating the biological processes that cause rot, but to the band she needed. Reliably between 35 degrees Fahrenheit and 42 degrees Fahrenheit, cold enough to slow respiration in the vegetables and inhibit bacterial activity, warm enough that nothing froze. She had worked this arithmetic out over 2 days of sitting in the main cabin, watching the fire and thinking about what she needed. What she planned to do, worked out over those 3 days of walking and probing and sitting by what warmth the main cabin managed to hold with 2 small fires she built from deadfall, was this. Connect the 3 structures underground. Dig a pair of shallow trenches between them. Line the trenches with the flat sandstone pieces she had seen eroding from the hillside outcrop above the tool shed. Cover the channels with more stone and with replaced earth, and use the resulting underground passages in 2 ways simultaneously. The first purpose was as a physical connection between the buildings, so that she did not have to walk 40 feet across an exposed Montana hillside in a blizzard to move between her living space, her workspace, and her food storage. The second, and more important, was as a warming system. Air moving through 40 feet of underground stone channel, surrounded at every inch by soil sitting at 48 to 50 degrees Fahrenheit, would not arrive at the far end at 32 degrees Fahrenheit. It would arrive substantially warmer, not as warm as the soil, because heat transfer takes time and distance, but warm enough to change the thermal arithmetic of the tool shed and the root cellar annex entirely. And warm air fed into any sealed space, a single central heat source would reduce the demand on that heat source. She could make 1.5 cords of firewood last twice as long if she cut the heating demand in half. And she could cut the heating demand in half by feeding pre-warmed air into the system instead of ambient winter air. The spade in the tool shed was a good one, German-made. A socket tang design that held without wobbling, the blade still sharp enough to cut cleanly through the upper layer. She set the fence post aside and worked with the spade from the first morning, cutting a trench 18 inches wide and 20 inches deep. The first 13 to 14 inches came up in the dry, crumbly freeze layer material, which she piled on the east side of the trench. Below that, the dense clay came up in solid blocks, each one weighing 6 to 8 pounds, and these she piled separately to the west because she would need both types of material later. The total trench she needed to dig ran 82 linear feet, 38 feet from the main cabin to the tool shed, and another 44 feet from the tool shed to the root cellar annex at an angle. The tool shed would serve as the midpoint of the system, the junction between two connected segments rather than one long tunnel. 82 linear feet of trench at 18 inches wide and 20 inches deep represents approximately 24 cubic yards of material. At roughly 80 to 90 pounds per cubic foot for the dense clay subsoil, that is somewhere close to 3,000, 200 pounds of earth moved by hand by one person at age 72 in October in Montana, with the temperature already dipping below 20 degrees Fahrenheit at night. She worked 4 to 5 hours per day, stopping when the light failed in the mid-afternoon. She moved 8 to 10 bucket loads per hour, each bucket weighing around 35 pounds. In 9 days of digging, she finished the trenching on day 12. One day after Heinrich's deadline had technically passed, she had shifted the earth and piled it cleanly beside each trench, ready for replacement. And nobody had come to check on her during any of those 12 days, a fact she noted. There was a specific problem she hit on day 6 that nearly derailed the second tunnel segment entirely. The trench line between the tool shed and the root cellar annex crossed a section of hillside where the subsoil changed character instead of the dense, workable clay she had been moving since day 1. She hit a layer of angular gravel and small stones mixed with what appeared to be decomposed granite, beginning at about 16 inches of depth and running for roughly 8 feet of horizontal distance. The gravel did not come up in clean blocks. It poured back into the trench as fast as she dug it, and the sides of the trench in that section kept collapsing inward, filling in the bottom faster than she could empty it. She stopped digging for half a day and looked at it, then went to the tool shed and came back with 2 things: a short length of split pine board from the scrap pile, about 8 inches wide and 16 inches long, and the wheelbarrow. She used the pine board as a temporary shoring piece, wedging it against the collapsing gravel wall while she cleared the trench bottom, and she worked that 8-foot section in a different sequence than the rest. Instead of digging out the full 2 0-inch depth and then lining it, she dug only to 14 inches, laid the sandstone floor and wall pieces, capped them immediately with the flat roof stones, and then excavated the remaining depth around the finished channel rather than through it. The completed stone box was rigid enough to hold the gravel back once it was closed. She backfilled the section, tamped it, and moved on. The solution took an extra day. It also told her something she filed away. The channel roof bearing the weight of the backfill soil without flexing was a function of how tightly she had selected and fit the individual capstones. In the gravel section, where she had rushed the capstone selection to get the structure closed before the walls collapsed again, she had a 4-inch gap between 2 pieces near the midpoint. She packed it with dense clay and it held, but she spent an hour the following morning pressing her hand along that segment of the surface ridge, checking for any soft spot that might indicate a settling gap, and finding none. The sandstone for the channel lining came from the outcrop above the tool shed, where decades of weathering had produced a natural pile of broken slabs ranging from 8 to 16 inches across and 1 to 2 inches thick. She did not need to cut stone, she needed to select it. Pieces flat enough to lie level on the trench floor, pieces straight enough on one face to stand on edge as walls, pieces large enough to bridge the 10-inch interior channel width as a roof. She worked for 2 full days doing nothing but selecting and hauling stone, loading it into a wheelbarrow she had found stored in the back of the tool shed, bringing it down to the trench in loads of 80 to 100 pounds. The channel she built inside each trench was 10 inches wide and 10 inches tall on the interior. She laid flat sandstone pieces in a single layer on the trench floor, set thicker pieces upright on each side as walls, and bridged them at the top with the flattest pieces she could find, using smaller fragments to fill the gaps and chink them with the dense clay she had set aside. The resulting structure was a stone box sealed on 4 sides, roofed in stone, with the surrounding trench walls backfilled first with the clay layer and then with the original freeze layer soil, tamped down and surface raked so that nothing remained visible at ground level except a slight, even ridge running between the structures. Before she covered the channels entirely, she cut openings at each end, rectangular holes, 8 by 10 inches, cut through the lower wall of each structure at floor level, connecting the interior of each building to the corresponding end of the tunnel. The main cabin's north wall received the primary inlet. The tool shed received both an inlet from the first segment and an outlet into the second. The root cellar annex received the terminal outlet. Air could now flow passively from the main cabin through the tunnel to the tool shed, and from the tool shed through the second tunnel to the root cellar annex. The flow was not forced, she had no mechanical means of forcing it. It worked on the same principle as any draft system. Warm air rises, cool air sinks, and a pressure differential between warm space and cooler space drives a slow but continuous movement of air. With the tunnel openings at floor level and the structures partially sealed, the system would pull cabin-warmed air along the ground and through the underground channels by the simple physics of convection. The rate of flow would be slow, a gentle drift rather than a current, but slow flow through a long underground stone channel is more effective thermally than fast flow, because slow air spends more time in contact with the warm stone walls and absorbs more heat from them. The stove was the one problem she could not solve with a spade. The main cabin had an existing stovepipe collar and chimney hole. Someone had used the building as a heated workspace at some point before 1878 and had installed the pipe penetration then. But the stove itself was gone. Heinrich had moved the cast iron range from the main cabin to the bunkhouse before his mother arrived, because it was a good stove and the bunkhouse hands needed it. What he left her was an empty collar and a hole in the roof. She found what she needed in the root cellar annex. A small soapstone box stove that Franz had brought back from Virginia City in 1872 when he had gone there to buy a harness press, and come back with this as well, telling her it was a superior heating device for any room where you needed steady temperature without constant attention. She had used it for a few years in the kitchen, then replaced it with the larger iron range when the family grew, and it had sat in the root cellar annex, since then perhaps 15 years, sitting on its 4 cast legs, still sound, still sealed at every joint. Soapstone is a metamorphic rock composed primarily of talc, with enough magnesium silicate in its structure to give it a specific heat capacity of approximately 0.98 British thermal units per pound per degree Fahrenheit. For comparison, cast iron comes in at about 0.1 British thermal units per pound per degree Fahrenheit. That ratio tells you something important. For the same weight of material at the same temperature, soapstone holds roughly 10 times as much heat energy as cast iron. The stove weighed, by Dorothea's estimate, what a full-grown sheep weighs. She had said this to Arvid Schoberg, and he had recorded it for Elsa, as one of those details that stuck roughly 110 to 120 pounds. That 120 pounds of soapstone, heated over the course of a 3-hour burn to 400 degrees Fahrenheit, stores approximately 47,000 British thermal units of thermal energy in the mass of the stone itself. A cast iron stove of the same weight, once the fire goes out, returns to room temperature within 90 minutes to 2 hours. The soapstone at the same initial temperature stays above 150 degrees Fahrenheit for 8 to 10 hours, radiating warmth the entire time, requiring no active fire. That is the difference between waking up to a room at 35 degrees Fahrenheit every morning and stoking a cold stove from scratch, versus waking up to a room at 52 degrees Fahrenheit and finding the stove still warm to the touch. It is also, in practical terms, the difference between burning 6 to 8 pieces of wood per day and burning 3 to 4. Every piece of wood not burned is wood still in the pile, and every piece still in the pile extends how long 1.5 cords last. She moved the stove from the root cellar to the main cabin using the 2-wheeled handcart she found in pieces behind the tool shed, assembled with 3 bolts from a coffee can on the shelf inside. The cart was not designed for 120-pound loads on uneven October ground, but the terrain between the root cellar and the main cabin was relatively flat, and she moved it in stages over the course of an afternoon, resting the load on the cart at intervals, adjusting her grip and moving forward. She connected the existing pipe sections she found stored in the corner of the tool shed to the collar in the roof and fired the stove for the first time on the evening of day 8. The first thing she noticed was the heat coming off the stove face, not the intense, almost localized heat of a cast iron firebox during active burning, but a broader, gentler radiance, the kind that doesn't make the air directly in front of it shimmer, but warms the whole room evenly from a surface, sitting at a sustained 200 to 250 degrees Fahrenheit. Soapstone radiates primarily in the infrared spectrum, which is the same mechanism as sunlight. It warms surfaces and bodies directly, not by first warming the air. The room felt warmer than the thermometer would have suggested, because the radiant heat was reaching skin and clothing directly while the air temperature was still rising. By the morning of day 9, for the first time since she had moved into the cabin, the wash basin on the side table was not frozen solid when she woke up. The tunnel system was complete on day 12, 1 day past Heinrich's deadline, which he either did not notice or chose not to enforce, because nobody came to the cabin that day. Dorothea spent day 13 doing 2 things: sealing every gap she could find in the walls and roof of the main cabin using the mixture she had developed over the previous few days from the dense clay subsoil and the dried bunch grass she had gathered from the hillside above, and banking the exterior of all 3 structures with the sod she had cut from the trench excavations. The clay-grass mixture worked as a chinking compound because of what the 2 materials contribute separately. Clay is dense and water-resistant once dry. With low air permeability, a sealed clay joint does not allow air to pass through it the way dried mud does, because the clay particles pack tightly enough to block convective flow. Grass fibre, mixed into the clay before application, prevents cracking on drying by distributing the tensile stress of shrinkage across the fibres, rather than letting it concentrate into fracture lines. The combination had been used as a chinking and plaster material in earthen construction across Europe and North America for centuries. Dorothea had used it in Bavaria as a child, and she used it here. She worked it into every visible gap in the log walls with a paddle cut from a pine board, forcing it deep into the joints, smoothing the face and letting it set. The main cabin, by the time she finished, had log walls with an effective R value, approaching R9 inches the wood itself, and virtually no air infiltration at the joints, which by Montana frontier standards in 1889 was an exceptionally tight building envelope. The sod banking added something different. Sod cut grass side down, root side up, in pieces roughly 12 by 18 inches and 4 inches thick, was stacked against the exterior of all 3 structures around the perimeter, reaching 28 to 30 inches up the wall from the ground. Dry sod has a thermal resistance of approximately R1, 5 per inch of thickness, so 4 inches of sod banking, added roughly R6 to the lower wall assembly. More importantly, it eliminated wind penetration at the base of the wall, the zone where cold air infiltration is worst in any log structure, because the foundation to wall joint is rarely tight and the wall logs at the bottom are the oldest and most checked. The sod covered that joint entirely and added insulating mass right where heat loss was greatest. By day 15, all 3 structures had been sealed, banked, and connected. The tunnel system was buried and invisible from above. The restored surface soil showed nothing but a slight ridge between the structures, easily overlooked. The soapstone stove was running on its 2nd day and had not once gone cold overnight. The woodpile, which Dorothea tracked carefully, had given up roughly 1/8 of a cord, and at that burn rate 1.5 cords would last approximately 12 weeks, which is roughly when the worst of the Montana winter would be over. Heinrich's calculation had failed. It had failed because he had assumed she would heat 3 structures in the usual way, 1 stove per structure, burning through the wood at the usual rate. He had not imagined 1 fire, 1 stove, 1 thermal network connecting all 3 through the earth. He had given her the tools of her survival without realizing it. The tool shed with its abandoned soapstone stove, the hillside with its sandstone outcrop, the root cellar annex with its existing depth, and most importantly 11 days with nothing to do but think. The first serious storm of that winter arrived in the 2nd week of December, 1889. The Missoula Weekly Missoulian covered it in the December 20th issue, describing temperatures that had not risen above -10 degrees Fahrenheit at the valley station for 6 consecutive nights. On the hillside, with the northwest wind, it was colder than that. Dorothea's system handled it without drama. The soapstone stove burned its morning and evening fires. The tunnel system moved air from the main cabin through the earth and into the tool shed and root cellar, arriving at 48 to 50 degrees Fahrenheit, regardless of what the surface temperature was doing. The root cellar annex, which had sat at an uncertain temperature before the tunnel connection, now maintained a steady 38 to 44 degrees Fahrenheit, verified by the behavior of its contents, none of which froze, all of which were holding their quality. The potatoes she had moved there in the first week were firm. The dried apple rings hung exactly as she had hung them. The salt pork barrels had not shifted in temperature enough to affect the brine concentration. In early December, Heinrich came across the hillside to check on the cabin. He went inside. He looked at the soapstone stove, which he did not recognize immediately because he had not thought about it in 15 years. He looked at the interior temperature, which was noticeably warmer than he had expected. He looked at the woodpile, which had gone down by less than he had calculated it would. He did not look at the floor, where the tunnel opening was covered by a piece of canvas Dorothea had laid there 3 weeks earlier without comment. He did not walk to the tool shed. He did not walk to the root cellar annex. He asked if she was managing. She said she was managing fine, and he left. What he had seen was enough to register something. His mother was warmer than she should have been and using less wood than he had expected, but not enough to explain it. He had assumed some efficiency he hadn't accounted for and did not guess tunnels, because tunnels did not come naturally to a man who had never needed to think systematically about heat. The storm that defined that winter hit on January 9th, 1890, and held for 4 days. The Fort Missoula station, less than 20 miles from the Krause property, recorded -35 degrees Fahrenheit on January 9th, and did not return above -20 degrees Fahrenheit until the morning of January 13th. The Missoula Weekly Missoulian would describe it on January 17th as the most prolonged siege of cold yet recorded in the valley. The wind sustained at 28 miles per hour through the 10th and 11th, dropping to 15 on the 12th before the temperature finally began to rise. At 28 miles per hour and minus 35 degrees Fahrenheit, the wind chill is approximately minus 70 degrees Fahrenheit, a number that stops being a description of cold and starts being a description of a different physical state of the world. Metal contracts. Wood shrinks. The log walls of a structure that seemed adequately chinked in November open their joints as the timber contracts in the deep cold, and air finds paths through that were not there a month before. A fire that was sufficient in December may not be sufficient in January, because the delta, the gap between inside and outside temperature, has widened from 80 degrees to 110 degrees. And every additional degree of difference costs proportionally more fuel. And cast iron, at temperatures below minus 40 degrees Fahrenheit, loses a meaningful portion of its impact resistance. The alloy structure of grey cast iron undergoes what metallurgists call a ductile to brittle transition. At low temperatures, it does not bend under stress, it cracks. This is documented extensively in records of frontier Montana winters, in accounts of stove components that held through mild winters and failed in the severe ones. The failure mode is typically a hairline fracture in the firebox wall that propagates under thermal cycling, the expansion and contraction of repeated heating and cooling until the structure splits. On the night of January 9th, the cast-iron stove Heinrich had moved from his mother's cabin to the bunkhouse cracked. A hairline through the firebox wall was evident in the morning, when the bunkhouse hands lit the fire, and smoke began seeping through the fracture, rather than rising through the chimney. By evening the fracture had widened to a full split, the firebox integrity was gone, and the stove was finished. Heinrich had 2 ranch hands wintering on the property, Arvid Sjöberg, who was Norwegian-born and had been working the Krause ranch for 3 years, and a second man named Karl Dahl, who had come on in the fall. He moved them into the main house, where the kitchen range was already being pushed to its limits, keeping the interior above 48 degrees Fahrenheit, with the northwest wind at 28 miles per hour and 35 degrees Fahrenheit outside. Adding 2 men's body heat helped slightly but did not solve the problem. The bunkhouse, empty now, was an icebox. On the morning of January 11th, the second full day of the storm, Heinrich walked up the hillside to his mother's cabin. He knocked on the door, she opened it, and the warmth that came out of the doorway was, in Arvid Sjöberg's words as recorded by Elsa, like putting your face near a fireplace. The interior was sitting comfortably in the upper 50s, possibly touching 60 degrees Fahrenheit. The soapstone stove was not actively burning, it was in its long, radiant phase. The fire from the previous evening's firing still lived in the mass of the stone, still releasing the 47,000 British thermal units it had stored, releasing them slowly and evenly, without any new wood being consumed. A cast-iron stove would have been cold metal by this hour. The soapstone was still warm enough to rest your hand on. The woodpile had gone down by a cord and a tenth in 3 months, and he still had a third of a cord remaining. Heinrich asked whether Dorothea had anything he could use to patch the cast-iron stove. She told him she had no cast-iron compound and no way to cast a repair, which was accurate. That type of repair required either a foundry or a specialized cold weld material that was not available rurally in 1890. He looked at the stove. He looked at the pile of wood. He did not look at the tunnel opening behind the canvas on the floor. He left. 2 days later, on the morning of January 13th, when the temperature had finally begun its slow climb back toward minus 15 degrees Fahrenheit, Dorothea walked down to the main house and knocked on the kitchen door. When Heinrich opened it, she made a specific and deliberate offer. If the ranch hands wanted somewhere to work on equipment during the day, the tool shed was available. It was warm enough to work without gloves, and they were welcome to use it. Arvid Sjöberg came that same afternoon. He came expecting to find a cold outbuilding made slightly less cold by proximity to whatever his employer's mother was doing up there. What he found, when he pushed open the tool shed door from -25 degrees Fahrenheit outside, was a room at 52 degrees Fahrenheit, with no visible fire source, no stove, no lamp, no heat-generating mechanism of any kind, that he could see just warm air, steady, reliable, persistent warm air, in a building 40 feet from the nearest fire. He stood in the doorway for a long moment, then went in and closed the door behind him. He spent 4 days in that tool shed during the remainder of the January storm. He repaired 3 sets of harness leather that had been stored in the bunkhouse and had begun to stiffen and crack. Leather at 20 degrees Fahrenheit loses its flexibility and will split under tension. At 52 degrees Fahrenheit, oiled and worked, it regains it. He sharpened every blade on the property. He serviced the hay press components, which required oil warm enough to flow into the fittings. He later told Elsa, 30 years after the fact, that he had thought about Dorothea's setup nearly every winter since, and had described it to anyone who would listen. He had never been able to fully explain to people why the tool shed was warm, and he was not sure he fully understood it later either. But he knew it was warm, and he knew she had made it that way, and he thought that was worth saying. What Dorothea had applied the movement of air through a buried stone channel, using the Earth's own stable temperature to pre-warm incoming ventilation, has a name in modern building science. Earth-air heat exchangers, sometimes abbreviated EAHE, sometimes called ground-coupled ventilation, or in older European literature, a passive earth cooling and heating tunnel. The engineering principle is the same regardless of what you call it. Air drawn through a buried channel at sufficient depth arrives at its destination at a temperature much closer to the stable soil temperature than to the outside air temperature. The longer the channel, the deeper it runs, and the closer the airflow is to the channel walls, the more effective the exchange. In modern EAHE systems designed to current passive building standards, a pipe buried at 6 feet of depth and running 80 to 120 feet can deliver incoming ventilation air, pre-warmed to within 8 to 12 degrees of soil temperature year-round. In Minnesota, where the soil at 6 feet holds 47 degrees Fahrenheit, that means incoming winter air arrives at 40 to 45 degrees Fahrenheit rather than 20 degrees Fahrenheit. The reduction in heating load is 30 to 40%. For the ventilation component of the thermal budget achieved without any mechanical system, without electricity, without filters, compressors, or refrigerant. The earth provides the conditioning, and the pipe just moves the air through it. Dorothea's sandstone channels ran at only 14 to 20 inches of depth, rather than the modern standard of 6 feet, which reduced their effectiveness compared to a deeper system. But she compensated in 2 ways. She did not realize she was compensating. Sandstone has a thermal conductivity of approximately 1.7 watts per meter Kelvin, roughly twice the conductivity of the packed clay soil that surrounds it, and higher conductivity means faster heat transfer from the stone walls to the moving air, which partially offsets the reduced ground temperature available at shallower depth. The flow velocity through her narrow 10-inch channels was also very slow, barely a drift, which gave the air more time in contact with the warm stone than a faster flowing system would have allowed. Slow air in a narrow channel near warm stone is actually more thermally efficient than fast air in a wide channel, for exactly the same reason that a slow-moving river picks up more sediment than a fast-moving one. Contact time is the variable that matters. The Passive House Institute in Darmstadt, Germany, which sets the international standard for ultra-low energy construction, includes EAHE as a recognized component of its passive ventilation framework. Scandinavian farm construction of the 18th and 19th century routinely used earth-bermed foundations for the same thermal reason Dorothea banked her buildings with sod. The Roman hypocaust, the underfloor heating system used in bathhouses and wealthy residences across the empire, applied an adjacent principle. The space beneath the floor was a thermal distribution network, warmed by a single furnace and moving heat through the structure by convection. The Anasazi cliff dwellings of the American Southwest achieved thermal stability through a combination of stone, thermal mass and earth sheltering that maintained interior temperatures 30 to 40 degrees above the winter ambient, without fire, purely through the physics of the rock and earth surrounding the spaces. Dorothea did not know any of these precedents. She had not studied engineering. What she had was a specific and extensive practical knowledge of how heat and cold behave in the world she had lived in for 72 years, and she had paid closer attention to that world than the men around her had paid to her. By February of 1890, the situation on the Krause hillside had arrived at an arrangement that bore no resemblance to what Heinrich had planned when he put that envelope on the table. The main house was running its kitchen range at near capacity through every cold night, and even then the far rooms dropped into the low 40s. The bunkhouse was empty and frozen. The cast-iron stove sat cracked and useless. The tool shed, connected through 38 feet of sandstone channel to a 120-pound soapstone stove burning less than half a cord of wood per month, held 52 degrees Fahrenheit around the clock. Arvid Sjöberg spent most of February in it. Karl Dahl joined him after the first week. They moved equipment, repair and maintenance operations entirely there for the remainder of the winter. Dorothea did not charge them for the warmth, did not impose conditions, did not extract acknowledgement. She made coffee in the mornings in her cabin and left the pot near the tunnel outlet so it stayed warm. Sjöberg said later that this detail, the coffee pot, was the one that made him understand she was not making a point, she was just living. What the two men encountered, working in the tool shed through February, was a room that had no business being warm, but was. They could not see the channel. They could not hear anything operating. There was no smoke from the tool shed, no pipe, no external sign of any heat source. The warmth simply came through the floor-level opening in the east wall, steady and reliable, at whatever the tunnel delivered that day, which ranged between 48 and 54 degrees Fahrenheit, depending on how long the main cabin stove had been running. On the days Dorothea fired the soapstone for its full morning cycle, the tunnel outlet in the tool shed pushed 54 degrees Fahrenheit air continuously for 6 to 8 hours. On the days she ran a smaller fire, the outlet ran cooler but still above 48 degrees Fahrenheit. The range was narrow and the consistency was what mattered. Sjöberg's account, as filtered through Elsa's letter, described watching Karl Dahl press his palm against the tunnel opening on the first day he used the shed and hold it there for a long moment, feeling the steady pressure of warm air against his hand. Dahl had said nothing for a while, and then had said, in Sjöberg's recollection, that it felt like a cow's breath, which was not wrong thermally, because the tunnel outlet was delivering air at roughly the same temperature that a large animal exhales, for the same fundamental reason. The earth around the channel was acting as a biological scale heat source, slow and constant and independent of any external condition. Meanwhile, 200 yards down the hillside, Heinrich was burning through his kitchen range fuel at a rate that alarmed him by mid-February. The main house, with its original log construction and the drafty bunkhouse empty and sealed, was holding 48 to 52 degrees Fahrenheit in the kitchen and dropping into the low 40s in the east rooms overnight. He had sent to Missoula for a replacement cast-iron stove for the bunkhouse, but the order would not arrive until March. At the earliest, winter freight on the mountain roads was unpredictable in a severe cold spell. The two ranch hands were sleeping in the main house kitchen, which was warm enough but inconvenient in every practical sense. Dorothea was reading. She was sleeping through the night without waking to tend a fire. She was eating dried apples that had kept better than any she had stored in 15 years, and potatoes that were still firm in the third week of February when they should, by the standards of that winter and that cellar depth, have begun showing the slight softness that precedes cold damage. They had not. The tunnel's temperature stabilization had held the root cellar annex at 38 to 42 degrees Fahrenheit through the entire coldest stretch of the winter, never freezing, never warming enough to encourage early sprouting. Exactly the band she had set out to maintain. She kept the ranch accounts through February. Heinrich had sent word twice that he wanted them, and she had not replied. She would respond when he asked in person, and he had not done that yet. In March, when the worst of the winter had passed and the snowpack was beginning to settle, Wilhelm came from Butte. He came without announcing himself and walked the hillside alone before going into any of the structures. He went into the main cabin, which was warm and occupied, and had a half cord of firewood still stacked against the wall. He went into the tool shed, which was warm, and had 2 men working in it without coats. He crouched at the tunnel outlet in the tool shed floor and pressed his hand against the sandstone edge of the channel and felt the warmth coming through it. He stayed there for a moment, then stood and went to find his mother. He told her he was sorry. The letter from Elsa does not record her response beyond saying that she made him coffee and he stayed for 3 days. It records that when he left, he went directly to Heinrich and said something what exactly Sjoberg either did not know or did not tell Elsa that changed the arrangement. Within 2 weeks, Dorothea had been formally recorded as a co-owner of the ranch property in the county land office. She was offered the east-facing bedroom in the main house, and she declined it, staying in the cabin for another 4 years, until the winter of 1893, when her eyesight had declined to the point where navigating the hillside in darkness and snow was genuinely dangerous. She moved into the main house, then into the east bedroom, which by that point had been repainted and had a new window facing south, added by Heinrich without being asked. She lived another 6 years, dying in 1899 at age 82. The tunnel system she built in those 11 days remained in use. Sjoberg maintained the stone channel lining through the 1890s, adding depth to the second segment when he expanded the root cellar annex in 1892. When Elsa visited in 1921, she found both tunnel openings still intact, the stone lining sound, the connections between the structures still usable as passageways, though no stove had been running in the main cabin for years. She put her hand into the tunnel outlet and felt it, warmer than the air above. There is a specific thing worth sitting with at the end of this story, separate from the engineering and separate from the injustice that started it. Dorothea Krause was 72 years old when her sons handed her an envelope. She was a woman who had kept a ranch running for 31 years, who had managed the accounts and the garden stores and the food preservation and the household logistics of a working cattle operation in one of the most demanding climates in the continental United States. Nobody had asked her opinion about the stove type or the root cellar depth or the way the bunkhouse was positioned relative to the wind. Those were men's decisions. The knowledge she had accumulated across those 31 years was simply assumed to not exist in a form worth consulting, and the envelope was an expression of that assumption. What she did with 11 days and a spade was not a miracle. It was applied observation, the kind that accumulates in a person who pays attention for 7 decades. She had watched the earth behave in specific ways under cold. She had watched what depth of storage kept food alive and what depth let it freeze. She had felt the warmth on a fence post pulled from 14 inches down. She had used that knowledge with the materials available to her, which were sandstone and clay and sod and an old soapstone stove that everyone had forgotten about because it was too small for the main house. She did not announce what she was doing. She did not explain it to anyone. She dug and lined and covered and sealed and fired the stove and waited for February. The physics she used is still in use. Earth-air heat exchangers are being installed in new passive buildings across Europe and increasingly in North America, designed by engineers with computational fluid dynamics, software, and thermal conductivity databases, achieving the same warming effect Dorothea achieved with a fence post and a sense of where the warmth was. The Passive House standard that governs the most energy-efficient buildings currently being constructed includes ground-coupled ventilation as a core passive strategy. Modern builders are rediscovering that you can move air through the earth and let the earth warm it, and that this costs nothing once the channel is dug. Dorothea knew this in 1889. The knowledge did not come from a textbook. It came from being old enough to have paid attention to the world for a very long time, in a culture that would not ask her opinion, and then was surprised by what she knew. The hillside in the Bitterroot Valley where the Krause property stood is private land today. Nothing marks where the tunnels ran. But the sandstone outcrop is still there on the slope above where the tool shed stood, still throwing off flat slabs of the reddish tan stone every winter as the freeze-thaw cycle works on the outcrop face. And if you drove a fence post into the ground on that hillside in January 14 inches down, through the freeze-cracked surface layer into the dense clay below, and pulled it back out and pressed your fingers against the tip, you would feel what Dorothea felt in October of 1889. The earth has not changed. The physics has not changed. And 11 days and a spade was always enough for the person paying attention.